Welcome to the High Energy Density Science Center Seminar Series. I'm pleased to have with us Professor Burkhard Militzer, who is a professor of planetary science at UC Berkeley. His research is focused on the interior and evolution of giant planets. As a member of the NASA missions Juno and Cassini, he studied the gravity fields of Jupiter and Saturn. He has a background in condensed matter physics and uses first principle computer simulations to predict the properties of materials at extreme temperature and pressure conditions. He received his PhD from the University of Illinois at Urbana-Champaign in 2000 and was a postdoc in the quantum simulations group at Lawrence Livermore until 2003. He was an associate staff member at the Carnegie Institute of Washington before joining the Berkeley faculty in 2007. So today's talk is being recorded, so if you are uncomfortable with that, please log off. And also please be aware it's an unclassified meeting, and we also have external visitors plugged in. And otherwise, please enter any questions that you have in the chat field, and I'll read them after Burkhard's talk. And otherwise, please enjoy, and I'm looking forward to this. Thank you.
Thank you very much, Paul, for the introduction. I would like to use the opportunity to give you some results from first principle simulations of matter in extreme conditions, and also would like to use the opportunity to talk about Jupiter's interior. That's what some of our activities are focused on. But most of all, I want to give you a little bit of a review how the groups in Berkeley have collaborated with theoretical and experimental groups at your institution. And also we had people who joined from William Berkeley and then went to Livermore. Kevin Driver is one of the examples. Shuai Zheng was a postdoc in Livermore and then moved on to a permanent position at LLE. We have François Ziboron, who went to the CAR. We have two new students, Tanya Kovacevic and Rustin Domingos, who are funded by our Center for Matter in Extreme Conditions, that is spearheaded by Farhad Beck at UC San Diego. And we collaborate with Livermore, with Heather Whitley, for example, Marius Millot and Damien Swift. And also part of our center are Sarah Stewart and Raymond Jonglo and Roger Falcone. So I want to use the opportunity to talk a little about what we've done so far. And hopefully that leads to a discussion about things we could do in the future. We had an earlier meeting earlier this week about possible things to do in the future. But let me just give you a little bit of a perspective what we've been doing, and then hopefully that leads to something else. So, in principle, I'm interested in planets as much as condensed matter as a whole. So these Juno missions and Cassini missions that actually visited these planets, each of them gave us a lot of homework to do, because we as theorists cannot predict all the complex things that happen on the planet, and you need spacecraft measurements up close. So in this talk, I will not go into details about the final results and the measurements in orbit around Jupiter, where the spacecraft actually went in between the rings and the planet itself and came closer and closer, and it actually burned up in Saturn's atmosphere. One of the main results that I found very exciting is that the winds that you do see on the surface are really, really deep, about 9,000 kilometers. And that was very, very unexpected. And they deform the gravity field of that planet, and the spacecraft picked it up. The spacecraft also measured how much mass there were on the rings, and the rings, as a result, are less than 100 million years old only. That's very surprising. So in Jupiter, I want to just talk to end about it, what the Juno mission that's currently in orbit around that planet has measured. And it gave us a lot of homework because the gravity coefficients, J4 and J6, came out extremely unusual. So we could not match them with these interior models. So every time we make a spacecraft measurement, we have to go back and revise your interior models. And this model no longer works. And it will tell you how we changed it. So overall, we are interested in matter in extreme conditions. That's Farhad's center. That's the goal. And here I'm just plotting temperature and pressure. I'm still sticking with GPA. That's 1,000 GPA, that or 40 megabars. That's where we approximately have Jupiter's adiabat. And there are a number of measurements now. When I started in this field, there were no measurements at that moment. Now we have many of them. Your CH done at Livermore, B4C, for example, also MgO and boron nitride, spearheaded by experiments at NIF and other facilities that really, really allow us for the first time to measure the equation of state and other properties, for example. So if you go higher and higher, you have these interior structures for different stars. So some of these measurements, like short-term CH, probed stellar conditions. Most exciting, I have to say, is one paper that came out very recently, spearheaded by Amy Lasicki, that showed that the diamond structure remains stable in the ramp compression experiments way outside the regime where density functional calculations predicted to be stable. So diamond persisted even when it was uniaxially compressed in such a ramp compression experiment. That's mind-boggling. So thank you, Amy, for telling us all about this unusual state of matter, which we theorists could have never predicted. And it's unusual in many, many different ways. For example, Felipe Gonzalez in our group, he performed simulations where you uniaxially compress diamond and then see when does this unit cell actually break down. And that happens way before you reach these extreme pressures. So our interpretation, what you might have seen, is actually a state where diamond in this structure not only remained stable at these extreme conditions, but also recrystallized. That's the interesting part. I don't think you can make such an experiment without recrystallization. So therefore, you uniaxially compress, the atoms have to rearrange, you recrystallize. And what you're telling us is recrystallizing in a diamond structure, even though the theory is saying it should be BCA. So that's very, very strange. So someone at Livermore has the capability to do carbon-based million atom simulations. I would like to know what happens if you really simulate this experiment. That would be an obvious thing to try, and maybe it leads to new understanding. So matter at extreme conditions continue to surprise us. And Amy, you just put a really, really nice example to that already exciting list. So today's talk, I want to sort of review a little bit why we use path Integral Monte Carlo, and then we combine in the equation of state, and we looked a little bit at silicates, for example, and then review the results, the predictions for CH and how they relate to the experiments done at Livermore. And I also like to convince you that the linear mixing approximation, it works actually quite well, surprisingly well for the equation of state. And then I'm tell you about the equation state database we put together. And finally, actually, I want to talk about Jupiter, which is probably not the foremost important object for you to study, but it's very close, very important for NASA because it was the first planet that formed the biggest, that coupled up most of the hydrogen helium gas, and then dominated the evolution through its gravity for all other objects in the solar system. So at low temperature, with low is maybe 1,000,000 Kelvin for heavy materials, or it's 10,000 for hydrogen. It's very light. In our group, we use, like many other groups, traditional density functional molecular dynamics simulations. And that allows us to get a reasonably good equation of state for this low pressure and temperature regime. For example, Jupiter's equation of state, what we rely on right now for the interior models that we construct is our ab initio results. At the present time, the experiments are not constraining enough to change the computer models that we construct for the Jupiter's interior. So I will explain why they're most sensitive and what you can do to make this better. And at high temperature, we switched to a very different technique. It's path Integral Monte Carlo, and that is based on Richard Feynman's work that originally invented it to study superfluid helium. And it's still a really good method to do so. But we apply the method now where the paths that are inherent in this method are actually the electrons. And that is a really, really good method to understand the electronic states and free electrons in a plasma state where you have predominantly have full ionization. The method is not so useful at the present time when most of your electron condense and occupy bound states. Then we have trouble for things I will mention in a moment. So the method was pioneered by David Zeppeli and Roy Pollock when they were at Livermore. So, and David Zeppeli moved on to Illinois later on, and some of his groups, including Hugo Paul, actually came back. So you have an active exchange among people within academia and Livermore. But nevertheless, we use this method that was pioneered for hydrogen in '96. So we moved on a little bit and now expanded these equation of state calculations. This was in collaboration with Suxin Hu at LLE. And he applied the Path-Angle method to really broad temperature and density regime, and you can study moderately degenerate conditions and weakly degenerate conditions. The interactions are treated quite efficiently, so there's no problem, but degeneracy, if it gets too degenerate, then the method has trouble. We also applied this method to helium and did it over a reasonable density range. And it turned out at that moment, if you're extremely high temperature, you get away with the Debye model. And intermediate regimes, path angles work really well. And at low temperature, we already coupled these results with density function molecular dynamics. And these equations of state fit reasonably well together. Even though one method works based on wave functions, and you can actually print them out from your code, and the other method, path angles, knows nothing about the wave functions, and it just prints, it works on path, and you move those paths around, but they're very delocalized, so they're probing this delocalization, which is also a feature of the wave functions. The physics of a Newtonian is all the same that is being probed, but that's why we get consistent results. But both methods have approximations, and therefore it's important to benchmark one against the other, and also to compare with laboratory experiments. So the path-angle method, you can most easily think about an analogy to the Boltzmann factor. So this takes us back to a quantum statistics course that you may have taken at some time. In classical mechanics, you have Boltzmann factor that tells you a state has a certain weight, and that gets scaled with the temperature. So the higher the temperature is, these highly excited states all of a sudden become partially occupied, and then temperature controls the effect. So if you know the partition function, then the problem is solved. You can just calculate all those observables while knowing the partition function. Well, if you switch over to the quantum world, then this density matrix operator, and you may choose to write it in position space, where you put an R and R prime on each end, and then you have two arguments here. At that moment, typically fall asleep, because they are sort of dealing with wave functions. You have one argument, but the density matrix, you have two. So at least I promise you there will be a few moments here where you're welcome to fall asleep, but that just needs to wake up for Jupiter. Most of the analytic work you can actually do with this density matrix if you know the eigenstates. Then it's just this expression here. However, in path-angle, we get observables computed with this method without ever writing down the complete partition functions or even knowing the eigenstates. The eigenstates, in typical fashion, you know them for non-interacting systems, and you typically do not know them as long as there are interactions in the system. So the method is a good way of studying interacting quantum systems. So how does the method work? Well, in principle, you just split up this density matrix by writing it as a product of different matrices. So this has some temperature, and then you write it as a product of m factors, and each of them has a yet higher temperature. So you're trading one problem for another, but the method becomes useful once you write it in position space, and then these different density matrices, you insert complete set of states, and then becomes a path-angle, because you start at some R, you have all these intermediate steps you have to integrate over because you inserted these complete set of states, and you have to end up in R prime. So this is like, you have to integrate over all path from starting from R to R prime. And the method is useful because you can describe these individual steps that take you from R to the next position at a yet higher temperature, and that is known more accurately. So at really, really high temperature, the correlations between different particles disappear. You are not important. You get away with two-body correlations, and the three-body correlations are not important at extremely high temperatures. But then these three and higher body correlations are recovered as you're evaluating this path. It's a beautiful method. You can basically do fully interacting system at any temperature that you want. If quantum mechanics hadn't told you have to do fermions and bosons, that makes it difficult. Nevertheless, before that happens, the method is essentially exact. So once we want to do fermions, David Zeppeli had an immense impact in establishing the quantum Monte Carlo method at 0 temperature. So now he also sort of designed the high temperature method by taking the following approach. You have this path here, and you take one point. Usually this is your reference point. It's usually put at R. And then you ask, if you knew the density matrix analytically, he basically said for this analytically given trial density matrix, all along your path angles, which is basically all possible paths, you're keeping those where the trial density matrix remains positive all the way along this path. So that is the fermion method, and we have not changed this approach ever since David Zeppeli and colleagues wrote it down for the first time. What we did change, however, what type of trial density matrix we put in here. So there's the simplest one for free particle nodes, but we went beyond, and that allowed us actually to incorporate heavier elements. So just to give you one example of this approach, let's just talk about magnesium sort of perovskite, magnesium silicon oxide. And here's one figure from a recent paper with Marius Mio. He measured temperature. So temperature measurements under shock conditions are very difficult, as we know. And therefore, it's useful to compare with results from ab initio simulations. And these are the DFT results here. So you get results within the error. There's a little bit of a deviation in temperature, but overall, I would call this a success. So the temperature measurements under shock conditions agree with the results from these density functional molecular dynamics simulations. That is a good step forward. It's not guaranteed it will work for all materials in all conditions, but nevertheless, here's an example where the agreement is quite good. So if we take this equation of state and extend it to higher temperatures, we eventually come to the point where we are the standard Cohen-Shum formulation of density functional theory is no longer applicable, or it's no longer practical, because you have just so many partially occupied states to consider. So therefore, we typically stop at 1,000,000 Kelvin for these heavy elements, and then switch over to path angles, and then compute the Hugoniot curves this way. So you have also isobars, and you have approximate isotropes you can calculate, but here are the equation state points with path angles, and here they are with density functional calculations. They're hard to do at low density because you have a plane wave expansion, and they're also hard to do at extreme densities because you would have to change to the potential. So this now, if you extend Marius Mio's work that was below here and go to more extreme conditions, you follow the Hugoniot curve, then you first come to the regime where the L-shell electrons are ionized. So this is a calculation where electron excitations were prevented. In this case, the Hugoniot curve would gradually rise to this 4-fold compression without ever exceeding 4-fold. So 4-fold you basically reach because you have electronic excitations of the L-shell. And then here we perform the calculation by preventing the K-shell electrons from ionizing. And in this case, there's another bump here. The path angle results take you in this regime where you're actually ionizing the K-shell, the innermost oxygen electrons. That again leads to another bump on the Hugoniot. And then you have 2 more K-shells, that of the magnesium and that of the oxygen, to ionize. And that is not to distinguish because they're relatively close in energy. It's sort of a broad maximum. It reaches a maximum compression about 4.7 before it actually goes back, eventually goes to 4-fold compression, unless you have relativistic electrons, then that makes this a contribution, or you have radiative effects. We're not doing radiative effects very carefully. We just use a free photon gas, and that gives you a very approximate way to see where they may be important. But in principle, you should take this with a grain of salt. This is just your reference. You go near the radiative effects. We don't claim to do very well. So nevertheless, what we've shown here is where the electrons electation becomes important. Here's the L shell and here's the K shell. So let's go back and take a material that's actually easier to do. It's plastic, it's just CH, and you don't have to deal with so many core electrons. So it's of course important for many of your experiments. This is a graph that Bachmann put together, and probably we have many of those seen before. What we've done with computer time at the Blue Waters machine in Illinois is to put together equation state tables for different carbon-hydrogen ratios. So we thought we could do this all once and for all. And for all of those, we did path angles at high temperature and DFT simulations below. So here were the existing experiments. They're quite large error bars. They were just not constraining for theory at the present time. In principle, I also have to say there's tremendous progress with shockwave experiments, let it be at the Z machine or at NIF or at the Omega facility, and they probe conditions that we couldn't probe before. But at the moment, we're still looking for experiments that actually tell apart different types of ab initio simulations. Maybe CH, we will see whether this already reached these states. We're also looking for an experiment that would probe whether the density functional correction due to finite temperature electrons matter. It would also be nice to have an experiment that shows this. So at the moment, the theory is making changes to the equation state, small ones, to the finite temperature electrons that are ingrained in the correlation effects. Nevertheless, let's come back here. These are the experiments by Bob Coble and colleagues at the Omega facility and at the Gecko laser that probe the Hugoniot states of hydrogen and helium shown here, sorry, of CH. And then this is the calculation that Schwarz-Zhang put together. You do see a small bump here. That is when the L shell electrons of the carbon atoms get ionized. You basically get they get promoted into the conduction band, but at these conditions, there's no longer a well-defined gap, and therefore you don't get a separate bump on the Hugoniot. So all you see is from the excitation of the L shell is this little shoulder here in the Hugoniot, and that big excursion here beyond fourfold is all due to the K shell of carbon atoms being to be ionized. Su Jinghu's calculation with orbital free density functionally gets a very gradual ionization. That's because there is no shell structure in the formulation that they use. And there are other curves put together by some of our colleagues here at Liverpool. So Thilo Döppner led the team that produced the first set of NIF experiments. And in these particular applications, we're dead on. We actually with really, really good agreement. And it's a regime where DFT seems to work quite well. This is where the regime where path angles work. You will see how we agree. And these are the results that were published in Nature by Annie Creature with the Liv Naser also. And there is a little bit of a difference here. So we're a little bit off. The theoretical, our path angle results here actually are within the 1 sigma error. So I would call this a success, but they're also a little bit off. We are a little bit more compressible, and the shape seems to be quite compatible. So we're good, but there's a little bit of a difference. So I'm sure this will be revisited. It will be measured again, and as these results become, these measurements become maybe a little bit more easy to do. This was the first time that Annie actually probed the Gbar regime for this material. It's amazing. So I'm really, really happy with the first one actually also to probe the conditions where we directly have path angle results. All the other experiments mostly probe conditions that are really, really covered with DFT. So what else did we do? Let me switch over to a team that was results that were done by Schwarz-Zhang and Heather Whitley that probed low Z materials, in particular boron, boron nitride, and boron carbide. And here I'm plotting the shock Hugoniot curves measured with these results here and here. And then I compared with the equation state tables that we put together using DFT and PIMC. So I'm bringing these things up for the very following reason. Here we have DFT and eventually have PIMC up here. We did one simple test. We just said, how about we try to reproduce these theoretical results by combining the equation of state of boron and nitrogen, because we had both of those sitting on our laptop. And also we had an equation state for carbon, and we also had that for boron. And now how about we combine those, and we just use this linear mixing approach and actually compare with the fully interacting equation state. So, and we got results that are really, really in good agreement. So there's some small deviations, but we get the maximum compression in the Hugoniot dead on, and for both materials. And even these experiments here, we seem to be getting away with using linear mixing. At conditions, there's about threefold compression. So here we see some deviations. So if you go below threefold compression, you see these linear mixing curves in blue that are different. And then the fully interacting simulations are slightly off. So we're not claiming this works for everything, but the whole rest of the material conditions works quite nicely. So this is surprising, right? So this is not supposed to happen. But in one case, you have a simulation where you have nuclei of magnesium and oxygen, which I will show you next, will interact with each other, and of course you have electrons. And you claim that you get the pressure and the internal energy that you derive, you can actually approximate it by performing a computer simulation of magnesium alone, where the magnesium atoms only interacting with other magnesium atoms, and the oxygens only interact with each other, and there's no magnesium-oxygen interaction. Obviously, you're leaving a lot of good physics out. So we have some background noise here. Can someone just mute the person? Thank you. So let's just test this for an even more strongly interacting material, like magnesium oxide, or basically enstatite, MgSiO3. So what we found was that this works extremely well again, as long as you're threefold compressed. You get the Hugoniot curve is really, really well represented. We have some small deviations here around this ionization regime, and we're not quite sure whether this is actually a nonlinear mixing effect or it's just the underlying equation to state or not. But basically, that taught us that linear mixing is really, really good as long as you're 3.2-fold compressed, or the temperature is like 200,000 Kelvin. This is amazing. This was unexpected. And if you ask anybody before, they would say, yeah, at high temperature, maybe that's true. But actually, the reason why it works at such a low temperature is that the energy scales, the energy error that you're allowed to make before you move the Hugoniot curve to a different location is so high, it's larger than the error that you're making by linear mixing approximation. So we published in this little paper here with our Livermore colleagues, and we also tested it rigorously in this paper. And we can sort of look what's the energy that we derive in linear mixing and compared to the full energy. And we divide by kBT, because otherwise the energy scales are too large. And then let's just see, for boron nitride, the error is really, really small. And then eventually, around 200,000 Kelvin, the energy increases. That's where bonds matter. We actually have bonding with nitrogen and boron, and they are not captured with linear mixing. That's why the error increases. It's very easy to understand. Same thing for MgO. You get an error at low temperature, but it really, really works at high temperature, where you have the regime of K-shell ionization. For MgSiO3, this is the concern here. This is not a linear mixing problem. This is a problem of the underlying equation state. So you can go to the paper and look at a few more tests, but nevertheless, the message here is linear mixing really works for threefold compressed materials. So that helps us theorists, because whenever you slightly change the composition of a material, you perform shock experiments, we don't have to redo all those calculations. We just use linear mixing. And it also may cut down a number of shockwave experiments. If you're just interested in the equation of state, you may not need to do experiment, except rely on experiments you perform for the individual elements. So that's actually quite useful. So let's just test it a little bit more. And here we've done so for carbon dioxide and carbon monoxide. So we never have done any simulation for those materials. Other people have, but we just now combine our equation state for carbon and oxygen. And these are the Hugoniot curves we predicted. So this is for CO in two different initial densities. This is our carbon Hugoniot. This is the oxygen, and this is CO. So we actually, there was a PL by Crandall, and the group was led by your former colleague, Rip Collins, and we always perfectly agree with their highest measured points that they predict. So if we get lower pressure points, we can't do this. But if you're along about threefold compressed, the agreement's pretty good. So we did, we also looked at H2O, and this is the linear mixing Hugoniot. You're mixing hydrogen and oxygen. So you have here the bump, that this is the oxygen K shell, this is the end of the oxygen L shell here. And we agree with the interacting simulations done by the Rostock group. And on our lowest trend, so basically they did fully interacting water, we just did linear mixing, and we think we could extend their Hugoniot curve. And we also agree with the reanalyzed results from Podorets, the Russian experiments, and reanalyzed by Markus Knudsen that shifted the Hugoniot curve a little bit over, so we agree with that point much better. So at that moment, we took a deep breath, and basically we looked back for the last 15, almost 20 years of Hugoniot calculations, and we had quite a good number. We had sodium, hydrogen, boron, and carbon, and lots of those individual elements, but we also had a number of compounds. So it was time actually to put it all together, to put a little database. And that's what we've done, and it's publicly available. There's a website, you can just download it here, and you can compile this very simple C++ code and run it. And I bet you, if you have a C++ compiler already on your laptop, if you download it now, you would have this database running before I finish my talk. So you're invited to do this. I will give you a little demo in a moment. We actually had one bona fide user, and this is Didier Zoumont. He is leading a team with Livermore colleagues here and my colleagues from Berkeley. We want to understand white dwarfs. So white dwarfs, they have a mixture of carbon and oxygen. And we want to, for the first time, do these NIF experiments for extreme conditions. And we're told you cannot put carbon monoxide or carbon dioxide into the as a NIF target material. So we have to work around it. And the proposal was, well, if you take acetic acid or you have glyoxal, they're both having equal proportions of carbon and oxygen, and just have a little of hydrogen. How would that change rather than doing CO would affect your Hugoniot states? So Didier just wanted to have a quick and simple prediction. How would your Hugoniot curves be affected? And he was one of the first users of our equation state. He basically installed it, and you have to type in FPEOS, say you want a binary mixture of carbon and CH, for example, and then he gives some additional parameter to characterize the initial state, and he calculated these Hugoniot states. So that was, and we sort of had a discussion whether we actually care about these different conditions that are probed. So that was not supposed to be a perfect calculation, but it was supposed to be something very simple. So I hope that some of you actually will be able to do this too. And I just want to give you a little bit example here. If you install this database, all you have to say to calculate an equation state for oxygen is to select oxygen and give it a starting density, and then you hit enter. And then the code will read that stored equation state table, will calculate the Hugoniot curves for you. And then at that moment, it's already done, and it calls Python to make some graphs for you. So this is as simple as it is. So I know in Livermore, you have a really successful division that does equation state calculation. So why would you even do this? Well, my hope is that it's so simple before you meet with someone like Phil Stern, who can do many more things than the simple equation state. You already tested it, and Phil Stern would ask, what did FPEOS give you? And this is basically what you get. You get a Hugoniot result here in pressure, in shock velocity and particle velocity. It prints the Hugoniot curves in pressure density space, and pressure and temperature density space, and pressure temperature space. It looks at the energy that's being predicted. It looks at pressure being predicted and compares with the Gbar model in these graphs here. So this is so simple. I hope that people will be able to use it very easily. So this sort of concludes my talk. The equation state database is useful because you can use linear mixing. It basically allows you, like for Zoumont, that you can mix different elements together, and then it broadens the scope. So let's just put this aside and then switch over. Why does it matter, and why I have some homework for you at Livermore to do. And this is the view for Jupiter's interior that we were started from before the Juno mission actually arrived and inserted in orbit around Jupiter. So we rely on theory. This is Miguel Morales's and colleagues' immiscibility curve. And that is still what we use in our simulations for the following reason. We know some helium rain must have occurred on Jupiter and on Saturn. And therefore, we have an issue adiabats we construct. So you start from some low temperature state at 1 bar, and you follow the adiabat, and eventually switch to ab initio results. And then you want to have an equation state that actually goes into your immiscibility region. So otherwise, if you have some other equation state that doesn't do that, then you're out of luck, because you cannot explain the spacecraft observation where some helium rain out was indirectly measured by comparing it to the solar composition, for example. So what else do we get? When the spacecraft flies by Jupiter, all propulsion is switched off, and the spacecraft by itself becomes the gravity probe. It receives a Doppler signal with ultra high precision, like a fraction of a millimeter per second. And that's being matched, and that information, the Doppler signal, is converted into a gravity field. And the gravity field is foremost 1 over r. But then there are these other coefficients in front of Legendre polynomials that show you the deformation of that gravity field from a perfect sphere. And of course, Jupiter's rapidly rotating once every 10 hours. So it's an oblate planet. It's 10% of the radius in polar and equatorial region is different. So that is also leads a signature in this first Legendre polynomial. We call this J2. That measures the oblateness of a planet, not the one you see, but the one you measure in the gravity. Then there's another coefficient, J4, and you can kind of visualize it. If you had an object that would look like that, it would have a strong J4 signal. And then you have J6 and J8, and all of those are measured to really high precision. And as theorists, we have to match them. Otherwise, if you cannot match these gravity measurements, something is not right with our interior model. So when you have a model, the first thing you have to decide, what's the composition? So you basically say make it of hydrogen and helium. You say maybe there was some helium rain out, just more helium in the interior. And then we typically say the planet is adiabatic, or to be precise, isentropic, because it's convective. So then you have helium rain, and then in the deeper part, you have more helium, and you have a core. So you put this sort of density structure into a code that solves for an oblate planet where you have two parts that contribute to the potential. There's gravity, and there's also the centrifugal force, which we convert into potential. And that code then solves for surfaces of equipotential. So that's Bill Hubbard's concentric Maclaurin spheroid method. And it basically decomposes the planet into 1,000 or 2,000 layers. And every layer is a layer of constant potential, constant temperature, constant density, and constant pressure. So that's how this works. And then we calculate, once we have the density and the shape, then we calculate this J coefficient. And then we do forward modeling, and we change the interior structure until we match. That was the perfect plan, we thought. And when we put together these models and we calculated J4 before Juno data was actually arrived, we were here. So we measured minus 955 for J4 and 35 for J6. And the Juno data was here. That was clear from 2 or 3 flybys that our models we constructed in preparation were not correct. And often in planetary science, you have had 10 models, they all fit the data, and you can't really distinguish. Here, which given with the challenge that something is missing. So the first thing that was missing from our models are the wind contributions. We learned that you have jets in the surface. You look at Jupiter's jets going left and right, and you have these ovals, you have a big red spot. They deform the gravity field because mass is involved. But nevertheless, when you do these calculations, they're not substantial enough to bridge that gap. So something was missing, and lots of people thought about it and had lots of trouble. And so it was very challenging. It took several years to solve this problem. The first inkling came relatively quickly. And before I explain, I just 3 easy way out. You can say there are no heavy elements. Heavy elements with like 1.5%. You can just change the equation of state. If you make it less dense, you can match Jupiter's gravity field. But there's no justification to make it less dense. If you use Quantum Monte Carlo, the one result from Guglielmo Martinak, I think, actually makes it more dense. Then with the planetary models are even more trouble. So then you could also make the interior more hot. If you don't start at this temperature of 166 Kelvin, then we can also match the gravity there. But we actually had a probe that was dropped in the Jupiter's atmosphere, and it actually measured 166.1 Kelvin. So it's also something we don't want to ignore. So why is there still a little bit of work to do? And the little bit of work is coming to the following fact. I have plenty of colleagues on the Juno team who worry about the atmosphere because we have a direct measurement. They can see it. There was a big ammonia plume that was measured. They really care about the atmosphere. And there were remote observations that measured that there are more heavy elements in the atmosphere than the sun has. And there was this Galileo Entry Probe that dropped in, and compared to solar, it measured that most of those heavy elements are enriched. And none of my models can accommodate this. Whenever I put a 3-fold enrichment into these models, nothing works. The gravity field is so different, the J's are so different, nobody can make this work. And we had sort of discussions what could be the reason. There could be a physical reason. There could be maybe the probe didn't measure what we think it measured. But the elephant in the room is the equation state of hydrogen. Because we use PB, one version of one particular functional, there's no reason to assume it is good enough to a percent level. But the challenge is we look for something that is less dense. If you make it more dense, then it's even more difficult to measure the spacecraft data. So the homework for you is we actually took our model and we asked if there is an equation of state in a particular pressure regime, where is this predicted heavy element abundance that everybody else on this mission wants to be high, increase a little bit compared to what we have right now. And that turns out to be the regime of between 10 and 100 GPa. So this is not the best graph I could walk you through, that's important, but if there is a pressure, there is a regime in this from 10 to 100 GP where there is an equation of state change, that's where the models are most sensitive. The density were less, then the abundance of heavy elements would increase. That's the only thing we can measure and we cannot match with current models. So that may sound like an easy problem for you Livermore folks because you're regularly probing gigabars, and now there's someone coming along and says, well, can you just probe 10 to 100 GPa? Well, I'm sure someone in Livermore can make such an experiment, but I want to just set the bar a little bit higher. So first of all, we would like to have the density, well, measured to better than 0.5%. And because solar abundance is 1.3%. So yes, 1% is good, but it should be really, really better than this. Otherwise, the error was maybe too large to change our models. And more importantly, you want to be close to Jupiter's adiabat, and you want to be on Jupiter's adiabat, or at least tell us what the temperature is. So we need a really precise temperature measurement to the density measurement, just a similar accuracy. I don't think anybody at these conditions can measure the temperature to 0.5%. And that's maybe the point where it's probably almost impossible to make that experiments right now. But if you have a clever idea how to get around this, this is the problem. Do not do gigabars in every time you make an experiment. How about you go a little bit lower in pressure and basically invest in a really accurate density and temperature measure. That would be really, really helpful for the planetary science community. All right, so this is all I wanted to say. I hope I illustrated a little bit what activities we currently have. They're either worked on the equation of state or they're basically focused on Jupiter's interior. So thank you very much.
Thank you. It's a very nice talk. So please enter your question in the chat field or let me know if you have a question. Otherwise, I welcome everybody to unmute yourselves so we can give Dr.
Thank you,
Militzer a
Frank.
nice
Thank you.
round of applause.
This is Bruce Remington. Can I ask a question?
Sure.
Burkhard, beautiful talk. It seems like for decades or maybe centuries, people have thought that the planets have a solid core. And now you're suggesting that for Jupiter, that's not the case. Is this widely accepted that the planets may not have, or at least that Jupiter may not have a solid core down at the very center?
So there are two parts to your question. So first of all, what happened here? So the traditional view up to, like, I would say 6 months ago was that there is a core of heavy elements. So this was what the models typically were put together. So that is the traditional view. So we're just hoping with our manuscript that we have submitted at the moment to overturn it. We basically said this discrepancy is evidence that there is a strongly diluted core, but this is not widely accepted. This is our work. This is our solution to bridge this gap. So what is probably accepted is that you do have helium rain that has been around for a long time, but people assumed when the solar system formed, there were lots of planetesimals. They collided. Jupiter was outside the ice line. There were lots of ice. That initial core grew very quickly, reached 10 Earth masses, and attracted all the gas. And then that was the bona fide internal. So that does not work because it puts you here. So now the question, the other thing you said, maybe not on purpose, you said solid. There is no clear understanding. You have to do a good melting line calculation. We don't know exactly what material this is, whether this is solid or liquid. And well, we say, well, it's diluted with hydrogen, where it's like 20% heavy elements, and the rest is 80% is hydrogen and helium. So it's definitely liquid, that's for sure. But even in a planet like Uranus or Neptune, where this is not given, is the question whether it's solid or liquid. That is unclear. You need an experiment, or you need a calculation to get the melting lines at these extreme conditions. And then it questions whether it matters. And it depends a little bit whether you can do seismology on the planet. So remember, the Earth's inner core is solid and was only detected with really measurements with seismology. But in principle, that is possible with giant planets if you observe the surface very carefully. So we'll see what happens.
Any other questions? Which other observables have you looked at, or have you focused mostly on equation of state?
For Jupiter? You mean?
Any elements? Path inter.
So, yeah, so the list that we put together was comprehensive. Then this is actually every material we've done so far. So we have a little trouble still going to yet heavier elements. So silicon we've done, but then if you we've explored a little bit chlorine. That was probably the highest one we've tested, and we're actually looking for another step in applicability where we yet again change the nodes or make the method overall more efficient to do iron in particular. So it may not be needed. John Pask and for example, developed the operator expansion method. So there's ways to extend density functional theory. So you may actually probe the regime of iron with other method. You may not need particles for these extreme conditions. So that's something that could be done in the future. At the moment, we are using path inverse, but it's difficult. It's basically difficult in the regime where either the heavy elements are, where the elements are too heavy, you have to deal larger fractions of core electrons occupying bound states, or you get in a regime where it's too low in temperature. So at the moment, I'm just showing what has been shown to work. And if I'm not showing it, that simply means that it hasn't worked yet. So yeah, so we haven't done iron, it's on the list, but we've done silicon, we've done tests for chlorine, but it's pretty much the limit what we can do right now. So.
Can you speak a bit about how you design the nodal surfaces?
Yes, so that is the crux of the method. That's basically where most of the invention go, where also your computer time goes, and where you need to invest your time. So traditionally, and that was done by Zeppeli and Pollock, used free particle nodes, and that works surprisingly well. It even works in a regime where you have a carbon atom. You have a carbon atom, the electrons occupy the 1s state. You have two of those, but they are not having the same spin. So there's no node as these two electrons occupy the K shell. And for that reason, even under these conditions, you get a reasonably good answer with just free particle nodes. But you do get better by introducing bound states into your nodal surface. And what we've done here is we used Hartree-Fock nodes, and Zhuai looked whether DFT or any version of DFT makes it much better, but it doesn't. Miguel Morales suggested we should have a fully self-consistent many-body wave functions put in. That's certainly possible, but at the moment, I'm not sure that's needed. At the moment, we are using Hartree-Fock orbitals for an atom. So you see, the crux of the method is right now, as electrons occupy these bound states, we have to get the core electrons mostly right. And therefore, we take that sum, which is sum over eigenstates for free particles. It's already by itself a complete set of states, but we're still adding for every nucleus the bound states. And that makes its two complications. It's very hard at that moment to move the nuclei around, because the shape of the nodal surfaces are now tied to the nuclear positions. And if you basically want to move a nucleus to a new location, you actually, the nodes are kind of dragged with it. And if the electrons nearby, all of a sudden, they weren't violating the nodes before, but now they do. So for that reason, we had to sort of put in a new type of move that looks which electron paths are nearby, and we want to move that nucleus. We look at how many electron paths are nearby, and then move those as we move the Monte Carlo, that nucleus. So we have different types of moves depending on what's accepted, but we had to indent these multi-particle moves because the nodal shape now depends on the location of the nuclei, while in free particles it doesn't. So we tried different things, whether it mattered whether you use the different types of nodes, but basically what we do is we have one nucleus and we just solve an atomic calculation beforehand, and then at those orbitals they don't know nothing about many-body physics to the nodes, and that seems to work reasonably well.
Is there a transition from free particle nodes to atomic nodes, like as you increase density?
We've not. So the density range we typically explore is like from, I don't know, 1/10 of ambient conditions to maybe a 20 or 50-fold compression. And in this case, there doesn't seem to be too much of a need to do that. So first of all, we're just building it on top of them. So when we say we do these Hartree-Fock nodes, we add them together for all temperatures. So they may not be important at very high temperature, but they're used at every temperature. They just matter more at low temperature. So therefore, there's no transition we have to choose. It's added for all conditions. And Yeah, in principle, you're right. If the pressures are too extreme, where these atomic calculations are no longer relevant, we have to maybe do something else. But even with 20-fold compression, we hadn't noticed anything drastic. So this is a simplistic approach, but it seems to do the job as far as we can tell.
Okay. Any other questions? If not, let's thank our speaker again.
All right, well, we'll see you around sometimes, hopefully in person at some point. Thanks a lot.
Yeah.
Thanks, Burkhard, for a beautiful talk.
Yeah, take care, Burkhard.
Happy Thursday, everybody.